We're now going to be learning about inflection points and the concavity test and walk through some examples. Concavity describes the curvature of a function's graph. If a graph is concave up, it curves upward like a cup. That kind of rhymes. Maybe that will help you remember it. When a graph is concave up, it starts out decreasing and then it increases. So that means that its derivative is changing from negative to positive, and that means that the derivative is increasing, which then means that the second derivative is positive. That's going to be really important when we look at the concavity test. When a graph is concave down, it curves downward like a frown. That also rhymes and it might help. When a graph is concave down, it changes from increasing to decreasing. So the derivative is positive and then it becomes negative. So the derivative is decreasing, and that means that the second derivative is negative. The concavity test is used to find where a function is concave up or concave down. With the concavity test, you have to look at the second derivative. If the second derivative is positive, then the function is concave up. And if the second derivative is negative, then the function is concave down. Another thing connected with concavity is inflection points. An inflection point, like the two down here on our graph that I'm just highlighting, is a point on the graph of a function where the concavity changes. An inflection point can be where a graph changes from concave up to concave down or from concave down to concave up. Let's now walk through some examples. We are going to find the intervals of concavity, and then we're going to find the inflection points for our function f of x. Just to make things easier, I have written down 4 steps that we can follow, and we'll go through these as we walk through our example. For our first example, we have the function f of x is equal to x to the 4th minus 4x cubed. Our first step is going to be to find f double prime, set it equal to 0, and solve for x. F prime of x is 4x cubed minus 12x squared, and then f double prime of x is 12x squared minus 24x. We are going to set that equal to 0, and we're going to solve for x. Looks like we can pull out a 12x, so we're left with x minus 2. And this gives us that x is equal to 0 and x is equal to 2. Now let's look up at our second step. We are going to find the value of f double prime to the left and right of each of these values of x. So I think the easiest thing to do is to go ahead and draw a number line. Here's our number line. We're going to put an x there, and we're going to put in the points x is 0 and x is 2. And we are going to be looking at the value of f double prime. So let me highlight f double prime, and that is this value right here. Because f double prime is a polynomial in this region and in this region to the left and right of our critical points, we can just look at the leading term to find the value of f double prime. It is an x squared, so it is positive. So we can say it's positive here and it's positive here. Now all we have to do is pick a point in the middle. I think the easiest point to choose would be that x is equal to 1, so we're going to find f double prime at 1. Looking back up to our formula in yellow, this is 12 minus 24. That is less than 0. Doesn't matter the value. We just need to know if it's positive or negative. And let's put a minus right here. Now let's look back up at our steps and look at step 3. We want to write down the intervals for concave up. That is when the second derivative is positive, or concave down when the second derivative is negative. I think it's easiest if we put a little graph on the number line that we've made. If we have a positive, it's concave up, and then we have concave down, and then we have concave up. Now it's really easy to write our intervals. So for step 3, it is going to be concave up on the intervals from minus infinity to 0 and from 2 to infinity. And then it's going to be concave down on the interval from 0 to 2. And let's go ahead and let's highlight those answers. There's our concave up, and there's our concave down. Now let's go back up and look at step 4. We want to write down the inflection points, and those are just the points where the concavity changes. The concavity changes at 0 and at 2. So this means we need to find the value of our function. Let me go ahead and highlight this in orange at the points 0 and 2. So let's write down number 4. We are going to calculate f at 0. That's just 0, so that's nice. And then f at 2, that is going to be 2 to the 4th minus 4 times 2 cubed. This is 16 minus 4 times 8. So this is 16 minus 32, and that's minus 16. So we can say for f of 0, we have an inflection point equal to 0, 0. And we'll highlight that. And then for x is equal to 2, we have an inflection point equal to 2 minus 16. And we'll highlight that. Before we go on to the next problem, let's look back up here at our graph. We found that we have inflection points at 0 and at 2. Those are those points right there. And then our concavity changes to the left and right of those points. We have concave up in this region, and then we have concave down, and then we have concave up again. Let's now look at our second example. I wanted to do a trig one for this example. We are given the function f of x is equal to cosine x, and we are given the region from 0 to 2 pi. Our first step is to find the second derivative. F prime of x is the derivative of cosine, which is minus sine x, and then f double prime of x is the derivative of minus sine, which is minus cosine x, and we're going to set that equal to 0. Between 0 and 2 pi, cosine is going to be equal to 0 when x is pi over 2 and when x is 3 pi over 2. These points then are possible inflection points. In step 2, let's draw a number line, and we'll put these points on it. We have pi over 2. We have 3 pi over 2, and then we are going between 0 and 2 pi. We now want to find the value of minus cosine x in all three of those regions. In our first region, between 0 and pi over 2, cosine is positive, so that means minus cosine is negative, so we'll put a negative here. Between pi over 2 and 3 pi over 2, cosine is negative, so minus cosine is going to be positive. And then between 3 pi over 2 and 2 pi, cosine is positive, so minus cosine is negative. So we're going to have concave down, and then concave up, and then concave down. Step 3, we just have to write down our regions of concavity. So we can say that it is concave down on the region from 0 to pi over 2 and from 3 pi over 2 to 2 pi. And then it is concave up on the region from pi over 2 to 3 pi over 2. Now let's think about inflection points. Because the concavity changes at this point and this point, those are our inflection points. So we have to go back up to our original function, cosine x, and find the value of cosine at those 2 points. So we have f at pi over 2 is cosine pi over 2, which is just 0. So we have an inflection point equal to pi over 2 comma 0. Let's highlight that before we forget it. And then we do the same thing for x is 3 pi over 2. We have f at 3 pi over 2 is cosine 3 pi over 2. That is also 0. So we have an inflection point equal to 3 pi over 2 comma 0. Now let's go back up to our graph and highlight our inflection points. We have an inflection point at pi over 2 and at 3 pi over 2. And you can see on the graph that our function is indeed concave down in this region and this region, and then it's concave up in the region in between.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.